Good morning. So this is group 14, and my group mate Jarosla is not able to be around. She got some difficulties. So the multitask graph attention mechanisms for detecting obesity gene expression. So first of all, these are the contents of our presentation. The introduction, related work, problem statement, research, questions, and then the objectives, and then the contributions, methodology, the dataset description, and then the results for the different models, yeah, and then conclusion, and then an acknowledgement. So first of all, we'll give a background and introduction. So obesity is basically a multifactorial disorder where excess fat is accumulated by the body, and this is a problem that can actually lead to very severe situation. We're talking of death. Yeah. So causes the causes of the of obesity. We have the genes. The genes could of themselves be a problem. Then we have lifestyles of the different people, and then hormonal imbalances, and then how people actually feel. So then the points of emphasis, we are going to emphasize the genetic contribution to obesity because this is what our project is actually about. So machine learning in obesity regulation. So how are we going to do this? So we are going to be able to recommend personalized meals based on different people's genetic profiles, as we've already seen in the previous video. So key genes, we have the FTOMC4R PAG, and yeah. So how are we going to implement this? We're actually using random forest and then KNN to implement this model. But we have different models and their evaluations, but we chose this one. So then we also applying some multitasking learning. It's more where simultaneous predictions of obesity risk and optimum dietary recommendations. And then we could also have potential health outcomes based on the genetic and nutritional data. So the illustration is basically a common gene, how common genes are related to obesity. As you can see, we already went through that during our presentation of the topics. So literature review and then the current trends in research trends. Obesity is influenced by genetics and then environmental and then lifestyle factors. We've talked about that. Then the personalized nutrition. We can tailor dietary recommendations for anyone depending on their genetic makeup to combat this issue. So what is the role of machine learning in this case? So we are using it to analyze the vast data sets, the genetics, the dietary and healthy outcomes to identify the patterns and then be able to predict the best outcomes. So the challenges we've got we have the dietary privacy concerns, and then the genetics data was a bit hard to get because all we could get is a very large data set of about 8 GB, where we extracted the data that we actually need for the different genetics profiles. That was the biggest challenge we got, and then the need for robust clinical validation because this project would need a clinical validation to stand on. So the current research trends, we have the genetic variants strongly influencing metabolism, appetite, and fat storage. And as we had addressed in some of the earlier submissions, that we had actually talked about these 4 genes and how each of them affects genetics in terms of metabolism, appetite, and then fat storage and things like that. So machine learning models, for example, random forest and then collaborative filtering, deep learning, we can use all of them to predict obesity, but we've picked out the best. So techniques like CNNs, RNNs integrate multimedia data. Then we could use reinforcement learning based on the health outcomes. For example, the body mass index, the BMI. Data integration, we've combined data from the different data sets we had already addressed. And yeah, for example, Food Data Central, that is USDA, and then NCBI. So potential impact are precision-based strategies for obesity management, and then scalable machine learning driven solutions to address the global issue. So then the problem statements are the domain application problem, we have the lack of personalized nutritional interventions. The traditional approaches we can say have failed, okay, to some extent, not completely, but they've not achieved what is actually required. Then the complex interplay of the factors, obesity results from the interaction of genetics, metabolism, environmental factors, so things like that. And then we also have the public health impact. Obesity is a major contributor, definitely, For example, diabetes and cancers, among so many other things. So we have a need for precision-based strategies. And yeah, the computational problem, we have high dimensionality of the genetics data. Millions of nucleotide SNP, they're called SNPs, require efficient feature selection and dimensionality reduction techniques. So then we have the problem of imbalanced data sets. We already addressed that. Then integration of heterogeneous data, we also addressed that. Scalability and real-time processing. And then model selection and optimization, which has been one of the cores of this submission. So what are the research questions and objectives? So some of the research questions that come up high top, which genetic variants have the most significant impact on obesity? There are like 1,000 genetic variants, but why these four? So identify key genetic markers that can be targeted for personalized meals intervention. So these are the genes that highly affect obesity. That's what we are driving to. So how can genetic data be effectively integrated with dietary data to create personalized meal recommendations? So the solution is to develop for a robust framework for combining diverse data types to generate precise dietary meal recommendations. So what are the most effective methods for integrating the heterogeneous data types? We've integrated different data techniques for better model performance. For example, we have a combination of KNN and then the random forests. Then how can imbalanced data sets be addressed? We already talked about this one. Go deep into it. So then the research contributions, we're able to find those different genes. And then we use the random forest classifier with KNN to integrate them to actually implement the model. And then we also do using some pipelining because we have two different data sets that are being handled, not in the same time or not in the same exact way. So then our methodology, we definitely collected the genetics data, then gene sequencing, gene expression analysis. Then predicting the obesity risk, we already did this one. And then using multitasking learning, random forest, and then the KNN implementation to actually come up with a personalized meal recommendation. So then we also do the collaborative filtering and then do a meal planning. We generate that. And then we should be able to get feedback and then yeah, improve. So going through we already did data set description and EDA, yeah. And we talked about the fact that we use two different data sets from NCBI and then USDA Food Data Central. But taking a look at this, this is the evaluation of all the models, like all the different 10 models that we've actually evaluated. For example, the SVM has an accuracy of 0.81, has a very high precision and a recall of 1, and F1 score, then low precision, yeah, those are the evaluations actually. Then the neural networks and then random forest. Yeah, the random forest alone actually gives us everything. It gives us a score of 1, which is a perfect score. And I don't think that would be a good evaluation for our model. So then we went on to implement the random forest and the as much as it has a bit low accuracy, it has a very good precision, as you can see over here. It has a very good precision. And it also has a high recall than the F1 score, the low precision is there. Yeah, and the accuracy is actually a good one. Yeah, so going to the logistic regression, not the best method in this case because it performs very poorly when it comes to the medium class. And then, yeah, the medium recall is also very low. The XG boost genetic model, we have that accuracy, and then, yeah, but then it performs very poorly when it comes to the F1 scores and then the precision. Then we have the feed forward neural network. This performed generally well, but for the medium class, the recall was not good at all. It had 45%. Then going to the advanced feed forward neural network, those are the scores, but then it also performs very well when it comes to the medium class. And then the random forest plus the KNN is the one that tries to perform very well, plus the XG boost, but then the XG boost performed very poorly when it comes to the low class. So So we came up with that, and then so going to the output and then the expected results. These are some of the learning curves for some of the modules. But some modules are, for example, we have two SVMs implemented. So this is one of them, but we have them implemented in different methods. And yeah, these are the learning curves. But and then for the XGBoost, this is what we have: the regression, random forest. And then I want you to observe maybe the random forest and the KNN. Its performance is actually very good for all the three different classes. For example, as you can see, for the high and then low and then the medium. Yeah, then for the feed forward, this is the learning curve and it's not the best. So we're actually going with the random forest and KNN as we go. So then and then continuing with the outputs. These are, if you look at this, we have we have the logistic regression coefficients for the different classes, and as we can see, the different variants, and then the coefficient values for the medium class. For the sorry, this is the first one. So this is the low high class, then the medium class, and then the low class for the best risk scores. Yeah, and as you can see, the logistic regression for the last one, which is the low class, is actually more of to one side compared to the others. This implies that the medium class is a bit more balanced than the high class. It's okay. This is what we're driving at. It's that for all the different modules, you find out that the regression the classes are always for the high class. You find that many people are actually very obese, and many people are actually not obese. This medium class comes up a bit more balanced than the others. So that's why you see results like this. This is actually a real life scenario. And then we also have the meal clusters from the KNN band. We also have the meal clusters distribution over here. For example, as you can see, we have for the nutritional pipeline, we have the low classes, the medium classes, because this one is divided a bit into more classes. Yeah, and those are the results from the different meal clusters. Yeah, so after that, we could look at more outputs. For example, the first graph is a confusion matrix. This confusion matrix is specifically for the one that we have implemented, and that's the KNN and random forest classifier. Then looking at this, we have this is the learning curve. This is the learning curve. I think I've gone through it, yeah, at some point. And then this is the learning curve for it's actually this is the learning curve. I think it's self-explanatory. And then talking about this graph that actually has the false positive rate and then the precision rates, you find out that this green class is a bit consistent. That is the medium class, whereas the other classes score very high or to a very low extent. Yeah, then there's something I have to address a bit over here. Yeah, this is a for the regression class. I'm going back a bit. These are the false positives rates, and then for these two graphs, the regression and then the random forest and KNN, the graphs actually are for the positive rates and then the false positive rates, and then this is also the same for the random forest and then the KNN implementation. Yeah, so then the graph that has so many graphs is this is a graph of the nutritional frequency for the different meal clusters. As we have so many meal clusters depending on the concentrations of what they had for the different models. Yeah, and then you can see over here, this is the expected result. Like after predicting, we expect a description, and for example, this description for this particular genetic profile, we got grapes and then canned and then Thompson seedless and yeah, things like that. But as we had said, this nutritional data set is actually from USDA Food Data Central, which is American based. So this is generally the performance of if this is the performance of the random forest and KNN implementation after training. And then we can look at the training sizes and then the training accuracies and then the cross validation accuracies and they also listed. So then yeah, so that marks the end for the different model implementations and the results they were given. Then going to the conclusions and then the limitations. Conclusively, we are able to come up with a machine learning model that is able to recommend meals based off an individual genetic makeup. We extracted 5 key genes, as we already talked about that, from the different data from the genetics data set. Yeah, so then the limitations we got is that there, as I actually addressed this to some point, there is a case of extreme obesity and there is also a case of very low obesity. And this is a very common case. So you find that for the medium class, it's always a bit balanced. So the other thing is handling high dimensional genetics data and integration with the heterogeneous data types. That is a very big issue and limitation that we have. So while the system shows promise, extensive clinical trials are needed to actually validate its effectiveness on a real world stage and across diverse population. Because it could be working for one population, but then we try it out in another population and it doesn't come out very well since the genetics data the genetics data is parameter is how should I say this is actually comes like from one area. For example, we could say if it's Ugandan based, then the genetics data comes from people from Uganda. We haven't tested it out on genetics profiles from different regions, for example, maybe South Africa and things like that. Yeah, then the next steps would definitely be incorporating additional data types, which we have talked about, which is a bit one of the challenges we got. Then maybe developing unexplainable AI techniques to make model predictions more transparent and trustworthy to the users. Then evaluating the long-term impact of personalized nutrition and obesity management and metabolic health. So we also talk about implementing robust data privacy and mitigation strategies to ensure fairness and security. Uh, we talk about data privacy. Data privacy is one of the issues we're facing during getting the genetics profiles, as many people would not like to expose their genetic profiles, yeah, for such a problem. So then the acknowledgement, we have the NCBI for the provision of the genetics data sets where the genetics profiles were extracted. Then we also have a USDA food data central provides us with nutritional data sets contributing to the new recommendation side of the system. And I guess that marks the end of the presentation. Yeah, thank you.